Hello, and welcome back. Mrs. Saunders here. We're continuing our foray into differential equations by talking today about Euler's method. Yes, I know it looks like Euler's method, but it's pronounced Euler. And we're going to use Euler's method. It's a numerical approach to the solution, well, maybe an approximation of a complicated differential equation. In our study of differential equations, so far we've only been given a restrictive set of linear separable equations. However, there are many differential equations that just can't be solved for an explicit solution. You can't just get an easy y equals out of it. We used a graphical approach last time when we were looking at slope fields to sketch an approximate curve through a given point. And then I showed you a little bit of integration for an algebraic method of solving differential equations. And now we're going to explore a numerical approach for approximating the solution of a differential equation, and this is known as Euler's method. Recall that a differentiable function will display local linearity at a given point. If you zoom in close enough, any curve can look like a line. When you've zoomed in sufficiently to a small neighborhood around the point of tangency, it would be difficult to distinguish the function from its tangent line, and this is the basis for Euler's method. The slope fields that we worked with last time are our set of sort of signposts on the plane for any given starting point. And then you can calculate the slope at that point using the differential equation. The slope tells you the direction to travel on a small segment. If you move a small amount, then you can calculate a new slope from the differential equation. Then you can travel another small distance, and you just repeat this process, and you can approximate the actual curve. So, for example, we're sitting at point 1 right here. And in order to get to point 2, I'm going to move over some little distance, some delta x, to get to my x2. And then I'm going to start at my y value and add the slope times that little change in x to get to my new y value. And if I keep doing that, I can really get pretty close to the shape of the curve. So here's a quick overview of Euler's method for solving differential equations. Step 1, find dx, delta x, if necessary. Sometimes it's given. Solve the differential equation for dy. Substitute the values of x, y, and dx to then actually calculate dy. Find a new y and a new x, and then repeat. Example 1. Let y equals f of x be the solution to this differential equation, 2x plus y, with the initial condition f of 1 equals 0. What is the approximation for f of 2 obtained by using Euler's method with two steps of equal length starting at x equals 1? Again, that's a lot of words, but basically, we're going to approximate f of 2 by starting at f of 1 equals 0 with two equal steps. First thing we're going to do is calculate dx. How big is each step? Sometimes you can kind of just do this in your head. If we're starting at x equals 1, and we want to end at x equals 2, and we want to do it in 2 steps, then each step has to be 0.5. So a little bit intuitive, but sometimes you want to actually work it out mathematically. So ending point minus beginning point divided by how many steps you want to take. Then we're going to isolate dy, or the change in y. So I just took my dx and multiplied it over to the other side of the equation. So I've isolated dy, or change in y. And now I'm going to make myself a table to keep my thoughts and my calculations nice and organized. So here are the points on our little signposts. And we're starting with the point x equals 1, y equals 0. And we got that from this. F of 1 equals 0. Now our change in y, our delta y, is 2x plus y times delta x. So I'm going to take my x value, plug it in for x, take my y value, plug it in for y, and my delta x that we found, and plug it in for dx. So this says dy equals 1. My change in y equals 1. So to get my new y, I take my old y, which is 0, and add the delta y. So I've got 0 plus 1 equals 1. All right, now let's go back over here to x. And I know that my delta x is 0.5. My change in x is 0.5. So the new x I'm going to be working with is 1.5. And the new y I'm going to work with is 1. And now we just get to repeat the process. So we've scooched over and up just a bit. And now we're going to take my new x, plug it in for x, my new y, plug it in for y, and the same delta x, because that changes, plug it in for delta x. So from my y of 1, my delta y, or my change in y, is 2. So now I take my old y, add the change in y, and I get my new y of 3. And then back over here to my x's, I was at x equals 1.5. I'm going to add to that my delta x, or my change in x. I have a new x of 2 and a new y of 3. And actually, that's the end, because I wanted to approximate f of 2. And f of 2 is approximately 3. Example 2 says approximate 3 points on the solution curve to dy dx equals negative 3x squared y, starting at 0, 2, and using the delta x of 0.1. So this time, that was nice. They just told us delta x. Delta x is 0.1. dy, or my change of y, is going to be negative 3x squared y dx. Again, I just took my dx and multiplied it over there. And then I bring up my table. So let's see, we're going to try to get to 3 points. Our initial point is 0, 2. And so here we go. Just take my 0, plug it in for x, take my 2, plug it in for y, and dx, plug it in for dx. Do all the math, and I have a delta y of, well, 0. We didn't go very far. So old y plus change in y equals new y. And then old x plus change in x equals new x. So now I have a new point of 0.1, 2, and we do the process all over again. So this x gets plugged in, this y gets plugged in, and the same delta x. All right, so now we've got a little bit of movement. We have a change in y of negative 0.006. So old y plus my change in y gives me a new y of 1.994. Old x plus delta x gives me a new x of 0.2. And now I have my new point. And the process goes again. So these decimals are getting a little bit nasty, but thankfully we're done. So we have our final point. It wanted 3 points. We have our final point of 0.3 for the x value. and 1.970072 for the y value. Example 3. This is a table function, so it's a little bit different. For a function, f of x, it's known that f of -8 equals -5. So we have this initial point of -8, -5. Selected values of the derivative are given in the table below. So this table doesn't give us points because this whole bottom is a slope. See, this whole bottom area is f prime of x at the point, or at the x value that's above it. Okay, so it says, what is the approximation for f of -4? So we have -4 and something we're trying to locate, obtained by using Eulers' method with two step sizes of equal length starting at x equals -8. So we're trying to get from -8 all the way to -4, but with just two steps. So we'll have to go from -8 to -6, and then from -6 to -4, which means that my delta x is 2. Okay, here's my table. So I've got initial point of -8, -5, and then my dy is f prime of x, the slope, times d of x. So let's clean this up a bit. So at -8, what's the slope? Well, the slope is -5. So I've got -5 times 2, that's my delta x, equals -10. So my change in y is -10. So I've got my old y is -5, plus the change in y of -10 gives me a new y of -15. So now I have a new point, -6, -15. Now I do it again. So my dy this time is going to be -4, that's the slope, times dx. So -4 times 2 is -8. -15 plus -8 is -23. And then finally I get to my x value of -4. My y value at that point is -23, and we're done. We've approximated that f of -4 is about -23. And that's Eulers' method at a glance. It is, please remember, just an approximation, but the more you can zoom in, the more accurate your approximation. Thanks for being here.